Okay, so in this section, or sorry, not this section, in this video, we're going to wrap up section 2.6. And what we're going to do is take a look at the precise definition for limits at infinity and do one proof involving this. Now, I'm not going to really ask you to do anything with this. We've already sort of dealt with the precise definition of a normal limit back in section 2.4, and that's kind of where I want to keep that stuff. I'm mostly just doing this for reference, so you can see what the precise definition would look like. All right, so let's just, I'm going to read through it, and we're going to use a picture to sort of illustrate, but let f be some function that's defined on an interval extending from some finite number to positive infinity. Then the limit as x approaches infinity of f of x is equal to L means that for every epsilon greater than 0, there is a corresponding number n such that if x is greater than n, then the absolute value of f of x minus L is less than epsilon. Okay, so this part right here looks exactly the same as our precise definition of a limit, this absolute value of f of x minus L less than epsilon. This part looks different. Notice there's no delta in this definition. Instead, it just says that there's some corresponding number n such that if x is greater than n, then this is true. And this is the part that indicates that x is approaching infinity. Okay, so depending on how small we choose epsilon to be, which again, remember, would indicate how close f of x is being brought to the limit L, n may have to be a larger and larger and larger number to ensure that this happens, which is kind of pushing that x, which is greater than n, out towards infinity. Here's an example of a graph that illustrates this. So you can see that this graph appears to have a horizontal asymptote at L. Even though the graph crosses through the line y equals L a few times, like we said before, it will eventually just approach it arbitrarily close as x increases towards infinity. So the idea in this theorem here is that you first choose an epsilon, which again, remember that epsilon determines an interval an interval centered at that limiting value L on your y-axis, okay? And that interval can be used to create this strip in the plane that we're seeing here. The idea is to find a value of n that's far enough out towards infinity such that all of the values past n trap that function in that strip, right? So you can see that this function, the curve, goes outside of that strip a few times, but then once we get past n, it stays confined in there, okay? And as epsilon is made smaller and smaller, that's going to shrink the size of this strip down, and you may have to choose n to be further out to ensure that the curve is trapped in that smaller strip. Okay, so that's the idea behind this precise definition. I'm not going to read through this second definition because this is almost the exact same. It's just the case where x is approaching negative infinity. If you look at it, the only real difference is that x is less than n in this part of the definition as opposed to being greater than n. And the definition implies a very similar intuitive picture of what the definition is saying, but this time x is approaching negative infinity as opposed to positive infinity. So what I want to do is use this to prove that the limit as x approaches infinity of 1 over x squared is 0. Notice this is just a special case of that theorem we already talked about. 1 over x to the r, where r is some rational number, will approach 0 when x approaches infinity. But we want to see what the proof would look like in a special case, and then maybe you can sort of imagine what the proof would look like in a more general case, okay? So again, remember the idea with these guys, we always do some preliminary work. So we want an n, some number n, such that x being greater than n implies that the absolute value, now remember in our definition, the absolute value of f of x minus L. So f of x is 1 over x squared in our case, and L is 0. 1 over x minus 0, which notice this is the same thing as just x squared, same thing as the absolute value of 1 over x squared. We want that to be less than epsilon. But x squared is already positive, so the absolute value here is kind of unnecessary. I could say, or just 1 over x squared is less than epsilon. I don't need that absolute value if I know that it's going to be positive anyways. If I were to multiply both sides by x squared and divide both sides by epsilon, since both of those quantities are already positive, so that's the same thing as this. 1 over epsilon is less than x squared. Or if I take square roots of both sides, I know that that preserves this inequality as well. I get 1 over the square root of epsilon is less than x. Okay? Which can be written the other way around. X is greater than 1 over the square root of epsilon. But remember, we were looking for a number that x, whenever x is greater than that, this is true. So 1 over root epsilon is the value of n that would have worked here. Now we do the proof. Remember, we always say let epsilon be greater than 0 first, and set n equal to 1 over square root of epsilon. Suppose x is greater than n. Then, remember, we want to prove this under the assumptions that we just made. 1 over, the absolute value of 1 over x squared minus 0, which is equal to just 1 over x squared. Okay? Is going to be less than 1 over n squared. Now, how do I know that? Well, if x is greater than n, and if we're assuming they're both positive, which is kind of implicit in the assumption here because n is equal to 1 over the square root of a positive number. If x is greater than that, then it's also positive. If both of these numbers are positive, then squaring them both is going to imply that we still have the same greater than symbol here. X squared would still be greater than n squared. And then taking reciprocals of both sides of an inequality reverses the inequality. So notice we have a less than here instead of a greater than now. Okay? But if I did this again, if I took, if I use the definition of n now, this is equal to 1 over root epsilon squared, which is equal to 1 over epsilon. The reciprocal of epsilon would just be epsilon. Okay? And that's where we wanted to end up. The absolute value of 1 over x squared minus 0 is less than epsilon, which finishes up this proof. So therefore, the limit as x approaches infinity of 1 over x squared equals 0. Okay? Again, if you dreaded ever having to encounter one of these types of proofs again after finishing 2.4, don't worry, I'm not asking you to do anything like this. Just wanted you to see what it would look like in the case of a limit at infinity. But this will be all that we need to talk about for 2.6.